In electronics manufacturing, the most expensive defect isn't the one you find, it's the one you miss. A single issue caught early takes seconds to correct. The same defect discovered after shipment can cost thousands times more to fix. This is why modern PCBA production never relies on a single inspection at the end of the line. Instead, multiple inspection stages are built into the process, each designed to catch a different type of defect before it moves further downstream. In this video, we'll walk through some of the most common inspection stages inside a PCBA factory and explain what each one is designed to prevent. Let's get started. The first line of defense begins before a single automated machine turns on, targeting risks at the raw material stage. Incoming quality control verifies component-level integrity. By inspecting lead planarity and terminal finishes under magnification, technicians identify conditions that could compromise solderability later in the assembly process. Before production starts, operators perform a final material verification check, comparing component reel labels against production records. This step ensures that every feeder position contains the exact component specified in the bill of materials, eliminating costly loading errors. Following the setup, the line executes a first article inspection. Rather than checking individual materials, first article inspection verifies the entire automated configuration. Inspectors manually confirm the placement, value, and orientation on the first completed assembly. Only after the first article is approved is the line released for volume manufacturing. With the setup validated, the substrate enters the active surface mount line. Many soldering defects can be traced back to issues during solder paste printing. The primary risk here is volume inconsistency. Excess solder bridges during heating to cause short circuits, while insufficient paste results in fragile joints that crack under mechanical loads. To solve this, the SPI system projects structured light across the printed pads, measuring the exact height and volume of every deposit to intercept printing deviations before component placement occurs. After components are placed and the board passes through the reflow oven, the liquid alloy solidifies into permanent metallurgical bonds. During this high-speed thermal cycle, components can shift, lift, or stand completely upright, a defect known as tombstoning. To capture these surface-level errors, the assembly enters the post-reflow AOI system. Using multi-directional LED illumination and high-resolution cameras, the AOI software automatically compares the geometric features of every component and solder fillet against an established standard, immediately flagging anomalies like missing parts or polarity reversals for technician review. By this stage, most manufacturing defects have already been screened out. The remaining objective is to verify overall workmanship before shipment. After production is complete, every assembly undergoes a final quality inspection. Inspectors perform a visual audit to verify workmanship, cleanliness, component integrity, and any signs of handling damage before the product is approved for shipment. Depending on the product's complexity and reliability requirements, additional verification methods may also be included as part of the manufacturing process. Packages such as BGAs and QFNs hide their solder joints beneath the component body, making them impossible to evaluate with conventional optical systems. When customers require additional verification, the boards may undergo X-ray inspection. By penetrating the component package, the X-ray system reveals hidden solder connections and helps identify defects that cannot be detected from the surface. Functional testing provides another layer of validation. By powering the assembly and simulating real operating conditions, engineers can verify that key circuits, interfaces, and control functions behave as intended before shipment. The exact test procedure varies depending on the product and customer requirements. No single inspection can catch every defect. Each checkpoint exists because it protects against a different type of failure. Some verify materials, some evaluate solder quality, and others confirm electrical performance. Together, these layers of verification transform a bare PCB and a collection of components into hardware that can be trusted in the real world.